So thank you. So in this talk, we'll be interested in one of the, in the so-called relay channel, one of the classical problems in network information theory. And we will develop an upper bound on the capacity of this channel, which is tighter than the celebrated Cutset bound by using measure concentration. And if there are people in the audience who have attended the tutorial on measure concentration in the beginning of the program, hopefully this will give them a chance to see yet another application of measure concentration. I think in this case, a slightly unconventional one. And this is joint work with my postdoc, Shigang Wu at Stanford. Okay, so here is our setting. Okay, so we assume that there is a source that wants to communicate to a destination, and there is a third node in the environment, which we will call the relay, that is willing to help this communication. Okay, and the channels are Gaussian, meaning that the relay observes the signal transmitted by the source, corrupted by additive white Gaussian noise, and the destination observes the superposition of the signals transmitted by the source and the relay, again corrupted by Gaussian noise, which is independent of this noise at the relay. Okay, so this is a very natural model to model a wireless communication system where the source can be a base station, this destination can be your mobile phone, and this relay can be a Wi-Fi access point in the vicinity that's able to hear the signal from the base station and is willing to kind of help this communication so that you increase the communication rate, the end-to-end communication rate from the source to the destination. Okay, and the problem we are interested in is how to design this communication system, how to choose the mapping, the encoding at the source, what should the relay do, how should it map its received signal to the transmitted to its transmitted signal, how should the destination decode, so that you achieve the end-to-end largest reliable communication rate, which is what we call the capacity of the system. Okay? And this is an old problem in information theory. It has been formulated in the 70s. And there is a seminal work on this model by Ayfer and Gamal from 1979, which basically proposes two basic achievability schemes for the setting, decode forward, compress forward, which correspond to the two basic operations the relay can perform here. Okay, so the relay can either try to attempt to decode the message from the source and somehow re-encode it, and hopefully that helps to increase the end-to-end communication rate, or it can compress its received signal and try to communicate this compression. Okay? And their paper also develops a general upper bound on the capacity of the system, which is nowadays known as the Cutset bound. Okay? And if you see on the literature, if you look at the literature since Ayfer and Gamal, there has been a lot of interest in this problem, a lot of papers, especially over the last 20 years or so. But if you look at this literature, you will see that basically it almost exclusively focuses on the achievability side. Okay, so in particular, we now have many other relaying strategies for the setup on top of this decode forward and compress forward of Ayfer and Gamal, but the Cutset bound remains as the only upper bound on the capacity of this Gaussian relay channel. Okay, I should say that in the discrete memoryless version of this problem, where we assume that the channels are discrete in the sense that they have finite input and output alphabets, it's actually known that the Cutset bound is not tight. There is a result by I don't remember, Wei Yu and his co-authors, where they construct a very peculiar model and they build on the peculiarity of this channel model to exactly characterize capacity, which happens to be lower than the Cutset bound for that channel. But in the Gaussian case, which is the most natural model if you're talking about a wireless system, we actually don't know if this bound is tight or not. So we have nothing better than the Cutset bound, and this bound has been consistently used in these previous results as a benchmark for performance. Okay, and the goal of this talk will be to improve on this front. So before this, let me just state what the Cutset bound says for this channel model. Actually, I will concentrate on a simplified version of this model where, and this is without loss of generality, where we will assume that the channels in this first stage are symmetric in the sense that the noise that corrupts both of these channels have the same variance, okay? But they're still independent from each other. And we will assume that the multiple access channel from the source and the relay to the destination has orthogonal components, okay? Meaning that these two channels do not interact with each other, in which case, because this channel is kind of independent of all the other channels in the system, you can take it to be just a rate-limited bit pipe with capacity R0. And this is without loss of generality due to network equivalence developed by Michelle Efros and her co-authors. So the Cutset bound for this model will say the following: if a rate R is achievable between the source and the destination, then you should be able to find a random variable X that satisfies a power constraint, a second moment constraint. This is the power constraint you want to impose on the signal transmitted by the source, so that R satisfies both of these inequalities. It should be smaller than the mutual information between X and Y and Z, okay? And it should be also smaller than the mutual information between X and Y plus R0, okay? So essentially this bound bounds the rate you can communicate from the source to the destination by the maximal mutual information across these two cuts of the network. This is the broadcast cut, and this is the multiple access cut. And because the channels here are independent of each other, this mutual information between X, Z, and Y reduces to the sum of these two mutual informations here, okay? Very simple, and actually you can make it even further simpler by realizing that the X that maximizes the right-hand side here of both of these inequalities should be Gaussian, and you get this very explicit expression, okay? If R is achievable in this setting, it should be smaller than these two numbers here, okay? Where P is the power constraint at the source, N is the variance of these noises, and R0 is the capacity of this link, okay? So what we will prove is an upper bound on the capacity of this. We will basically show that if R is achievable in this setting, it should actually satisfy some more stringent constraints, okay? So you should be able to find an X again that satisfies a second moment constraint, and also a real number A, which is non-negative, so that R is smaller than this mutual information. This was exactly what we had in the first inequality in the Cutset bound. And then this, basically this sum here, these first two terms are exactly what we had in the second bound in the Cutset bound. But now we have this minus A term. And the role of this third inequality is to make sure that this A is strictly larger than 0, so that this bound is indeed tighter than the second bound in the Cutset bound, okay? And just like we did for the Cutset bound, you can write these expressions in a much more explicit form. Okay, let me skip this one. Essentially, it's pretty straightforward to arrive to this very explicit. The reason why I'm showing this more general form here is because this is what I'm going to prove at the end. But what this is saying is equivalent to this very simple expression here, which says that if rate R is achievable, it should be smaller than the minimum of these two numbers, where this A star is the solution of this equation here, okay?
0?
Because if A is 0 here, right, and it's 0 here also, this will make the rate smaller than the capacity of this point-to-point channel. So basically, the theorem says that if rate R is achievable, you should be able to find an A such that all these inequalities are satisfied at the same time. So in order to see what is the constraint imposed on R jointly by these two inequalities, you can see the following. This first term is the same, okay? So basically, the largest rate that these two constraints will allow together can be found by equating this to this one. Okay, it's just because the statement of my theorem says that if R is achievable, I should be able to find an A so that these two things are satisfied at the same time.
So let's go back one slide. Yeah,
Here, I also say the same thing. There should be, if a rate R is achievable, you should be able to find an X, and you should be able to find a non-negative A, so that all these three inequalities are satisfied at the same time.
But if you take A equals 0, which is potentially a claim.
The same thing again.
You get what you had before, right? Like
Yeah, but now I have this third inequality, right? If A is equal to 0, this part goes away. This will say that the rate is smaller than the point-to-point capacity, okay?
Yes, but then you get the Cutset bound, right?
No, like the rate cannot be smaller than that would say that the relay is completely useless, right? That's not true, right?
A is 0, why?
Because see this inequality, if A is 0, right? This is what I'm left with. Yeah.
You're right, so.
Is the second constraint not really dominated by the third one?
In the case A is equal to 0, so yeah. Maybe the way these things are stated is a little bit confusing. Like, so we should be really looking at maybe this one, which is just saying that if rate R is achievable, then it should be smaller than the minimum of these two numbers, and A star here should be the solution of this equation. And if R0 is non-zero, this means that A star is non-zero. And this is precisely, this first part is what we had in the Cutset bound. So this is immediately tighter than the Cutset bound, okay? Okay, so, okay, and if you wonder how tight, okay, basically what we did here, we looked for the largest gap between the Cutset bound and this new bound over all parameter regimes for this channel model, all values of P and N and R0, and you see that the gap is at most 0.05, okay, which is not too much, okay. But maybe it's not that small if you consider the fact that if you look at how much the Cutset bound can deviate from just the point-to-point capacity of the source destination link without the relay at all, this difference can be at most 0.5 bits. So then this improvement is kind of 1/10 of this difference. So in that sense, maybe it's not too bad, okay? And this was all obviously very specific to the single relay channel, and one may wonder if this has anything to say for larger Gaussian relay networks with arbitrary topology, and indeed, yes. So for example, there is this in a recent, maybe not so recent anymore, approximation approach for Gaussian relay networks that was pioneered by Avestimer, Digavi, and Che, where basically they try to approximate the capacity of any Gaussian relay network with the Cutset bound within a gap that is ideally independent of the parameters of the underlying network, channel configurations and topology. And indeed, in their approximations, the gap depends actually on the underlying network, but only through the total number of nodes, okay? In the first approximation they were able to demonstrate was saying that you can approximate the capacity of any Gaussian relay network with the Cutset bound within a gap which is like smaller than 7.5 times the number of nodes in the network. And these approximations were consistently improved over the years, and I think the current best approximation we have is something like 0.5 N, okay? And now looking at these trends, okay, you may wonder how much can we continue with this trend, right? How much can we further improve these approximations? And in particular, can we get a sublinear approximation gap here, okay? And this was, I think, a question that wasn't quite clear for a while. It was mentioned in a couple of these works. What we were able to recently observe with Tom Courtade from Berkeley is that you can make a very simple argument to say that sublinear gap would be achievable in these approximation results if and only if the Cutset bound is tight for each and every Gaussian relay network, okay? And this was a nice IT paper from last year, but when we proved this, there wasn't really any example of a Gaussian relay network where we knew that the Cutset bound, where there was some gap, okay? But now that we have one, right, we can actually say that this linear gap in these approximation results is indeed fundamental in the sense that there are networks for which the difference between the capacity and the Cutset bound will be linear in n, okay? And moreover, basically, if you can establish a gap for one specific instance, this allows you to get a lower bound on this preconstant, okay? So what we are currently able to say is that we knew the gap could be made smaller than or equal to this number. We can now also provide a lower bound, okay? And I'll skip the argument. It's super simple, okay?
So that comes from general equality, or you need this orthogonality?
No, it's general, completely arbitrary. Yeah, I mean, this approximation approach here, what I talked about here is complete.
This is fine, but for the new lower bound.
No, actually, this is just saying that you couldn't, if you wanted an approximation which is general, okay, of the topology of the network of the channel configurations, the gap should be at least as large as this much. Yeah. Okay, in my remaining time, I would like to tell you about the proof, because I actually think the proof is more interesting than the result itself, okay? So for this, I'll have to tell you a little bit how one goes about proving converses in multi-user channels, and I'll briefly go through the derivation of the Cutset bound for this, and then I'll tell you how we deviate from that derivation, okay? So the Cutset bound works like this. So you want to develop a converse, right? So what you would assume is that you have a reliable code for communicating over this channel, which, let's say, has block length n and has rate r, and xn will denote the code word transmitted by the source from this code book. Zn will denote the observations of the relay over these n channel users. Yn is the observation of the destinations. And now In is the bin index chosen by the relay. Note that this is a rate constrained bit pipe, right, of rate R0. So over n channel users, I have nr0 bits. I can communicate nr0 bits. So this In is an integer that takes values from 1 to 2 to the nr0, okay? An integer random variable that takes values from 1 to 2 to the nr0, okay? And the first step, that's very standard, is to use Fanos inequality to say that if this code is reliable, then its block length times its rate cannot exceed the mutual information between xn and whatever observation the destination collects, which is this In and Yn, okay? And then you try to single letterize this, okay? Because this is too complicated. Okay, and you can single letterize this in two different ways. You take this n-letter expression. You can first upper bound it with this n-letter expression. This is simply because In is a function of Zn. Therefore, by the data processing inequality, this is larger. And then you can just use a time-sharing argument to single letterize that, okay? And you get your broadcast bound in the Cutset bound. In order to get the second bound, you start with the same expression, but now you will isolate this term, and then this is what you're left with, and you'll just write this as the difference of two entropy terms, okay? And you do something very simple. You say, this is an integer random variable that takes values from 1 to 2 to the nr0. So the entropy of this guy, even without the conditioning, can be always bounded by n times r0. And this is discrete entropy, so it can always be lower bounded by 0. Okay, and you simply, again, time sharing argument to single letterize this, and you get your Mach constraint. Okay. So what we will do is, instead of, so we will leave this bound as it is, okay, that was the same. But here in the MAC constraint, okay, when we are looking at this term, okay, first realize that I can actually remove the conditioning with respect to yn here, because this bin index, index chosen by the relay depends on yn only through xn, so it's independent of yn given xn. So this is the entropy of in given xn. So what we'll do is we'll just call this quantity something, okay? Say call it A, okay? And then we will try to prove a lower bound on A, okay? If I don't prove a lower bound on A, then this is just the Cutset bound, right? But before doing that, let me just tell you intuitively why you would expect this conditional entropy here to not be very small, okay? Why lower bounding it simply with 0 in the Cutset bound should be loose, okay? So think of it as follows. Assume this entropy was exactly 0, okay? What this would mean is that given xn, there is no ambiguity. Given the transmitted code word, I can say without any ambiguity what the relay, what the index chosen by the relay would be, okay? So this is saying that given xn, basically all observations of the relay that are typical with this xn, that are likely to occur under xn, should be mapped to a single index, right? So that we can deterministically know it, okay? But now observe that basically, because of the symmetry of the channel, so the typical set of yn and zn are exactly the same. And if this whole typical set is mapped to a single index, this means that the entropy of in given yn is also 0. Okay? So I can roughly argue that if this term was 0, this term would also be 0. Okay? And then I would be able to bound the rate with the single user capacity, which is obviously not true. Okay? So
the assumption that the noises have the same values is...
Yes, but we can actually, we have an extension. So this is something I decided to focus on for this talk, okay? Okay, what we would have to do in general is the following. We would rather want to fix this quantity to be something, and I want to show that I want to find an upper bound on this one, okay? That would be our general approach. Or what you can do is you can subtract the entropy, add and subtract the entropy of in here, and this will give you the mutual informations. What we are essentially doing is we are constraining this mutual information to be something, and we are actually trying to lower bound this, okay? And in doing that, note that in my argument for this case, when a was 0, I only use the fact that yn and zn are symmetrical, okay? And I use the fact that yn and zn are symmetrical, and in is a function, the index is a deterministic function of zn. Okay, so basically, when I'm like lower bounding this, I'll only use this Markov chain structure that is suggested by this by the channel structure here, and I'll use the fact that given xn, yn and zn are IID, Gaussian. Okay. And in this sense, there is some connection between what we are doing here and what with people interested in strong data processing inequalities do. Like, essentially what they're interested in is they want to take a Markov chain and they would fix the mutual information between this guy and xn, and they would want to upper bound the mutual information between in and yn. What we are doing is rather the opposite. We are fixing this mutual information and we want to prove a lower bound on this. Okay? Okay, so how do we go about this? Well, now a is non-zero. A is something arbitrary, right? Roughly speaking, this says that given xn, I now have some ambiguity regarding the index in chosen by the relay. Okay, so this is roughly saying that the typical set around, so given xn, the set of typical relay observations are now not mapped to a single index, but probably to multiple indices, okay? And I would ideally want to control this picture, basically the number of bins that this picture, this typical set is mapped to, and the probability of each bin, okay? But this is not possible to do because here by fixing this entropy, I'm constraining the average behavior of this mapping from Xn to In, and just by constraining the average, I cannot say anything about how this mapping behaves around every code word, okay? But you can say something if you do the following, and this is something very strange you never do in kind of developing converses for multi-user problems. We'll take these n-letter variables, okay? These are the variables induced by our reliable code, and they will have some joint distribution determined by the code itself and the channel structure, and we will generate B-length IID sequences from this distribution, okay? So now these are longer sequences, okay, that are IID from this distribution. They lie in an MB dimensional space, okay? And now I can apply the law of large numbers in this MB dimensional space, okay? Or typicality to say that now for a typical Xi pair in this NB dimensional space, the probability of I given X, the probability that Z is mapped to the ith bin given X, is just 2 to the minus B times this conditional entropy, okay? So this is just standard typicality. Okay, and now indeed I'm able to say that in this higher dimensional space, this typical set is indeed split into 2 to the NBA bins, and each bin has this much probability, okay? And then we'll apply measure concentration, okay? So I looked at the slides of Sudeep. Okay. I thought we started a bit late, so okay. Okay, so I looked at the slides of Sudeep and from his measure concentration tutorial, and it seemed to me that he emphasized more the functional picture for measure concentration. For example, this is one of the theorems he proved. So here, if you have an X, which is a standard Gaussian random vector of dimension k, and you have a function z, z is a function of x and f is Lipschitz, then you can say that z will concentrate around its mean exponentially fast, okay? Although this theorem looks kind of completely different than this one, this is kind of more or less the same thing. They're capturing the same thing, and this would be the kind of geometric picture behind measure concentration, okay? So this says that if x now is standard Gaussian, if you take any subset of Rk, and if you blow it up with a radius t, meaning that you take all points which are at most at distance t to a point in B, the probability that x doesn't lie in this blown up set is exponentially small, okay? And just to appreciate kind of the significance of this theorem, consider now a set which has exponentially small probability. This theorem is saying that if you blow it up by a radius which is quite small, it scales like square root of k, then suddenly the probability that x doesn't lie in this set is exponentially small, okay? So this is saying that the probability concentrates on extremely small sets, and therefore the name measure concentration, okay? And we'll apply this to our problem. So we know that for a typical x and I, okay, the probability of the ith bin given x is this much, exponentially small. And now I can say that if I blow it up with a radius which is not that big, then the probability that now z, the observation of the relay lies in this blown up set, is suddenly almost 1, okay? And because y and z have the same symmetric distribution, the probability that y lies in this blown up set is also 1, okay? And so why is this interesting? This is interesting because of the following. So a priori, for these n-dimensional random variables, you could trivially draw this picture. Given a code word xn, you know that yn and zn will lie in a sphere around xn of certain radius, and because the noises are independent, they will be orthogonal to each other in a typical configuration, and zn is mapped to in, okay? What we discovered via measure concentration from the previous slide is that in this MB dimensional space, given a typical xi pair, okay, for almost all the y's with almost probability 1, I will be able to find a point which is very close in Euclidean distance to this y, and it's mapped to the right bin, okay? So observe that when a is equal to 0 here, right, this would say that y itself is mapped to the ith bin, and this was exactly the argument I gave you when a is equal to 0. Now, when a is not equal to 0, I cannot say that this is mapped to the right bin, but I can say that there is a point which is very close in Euclidean distance that's mapped to this bin. Okay, and you can imagine that now that I know that y and I are in some sense close to each other, I can show that the conditional entropy of one given the other cannot be too large. Essentially, we translate this geometric picture to an entropy relation or an information inequality. We can bound the conditional entropy of yn given in, or this difference of mutual information. So we fix this one, and now we are able to say this should be large because these are close to each other, okay? And we have a bound in terms of A, which relates to this quantity, and this is precisely what gives you the last constraint, okay? You had a question or? Okay, yeah, so yeah, let me finish and then I'll take questions, okay? There are some interesting things, conclusions you can draw we have similar bounds for the discrete memoryless case, and we applied them to an open problem by cover, and it gives kind of some surprising results here that I wanted to talk about, but I don't think I have too much time, so I'll just conclude maybe by saying that, so basically we developed new upper bounds on the capacity of the relay channel, okay, that are tighter than the Cutset bound. And I think the most interesting thing here is that our proof used ideas like typicality and measure concentration, which is not something you typically use in developing converses for multi-user problems. But if you think about it, our approach is not really unnatural in the following sense, right? What we essentially did was there were these random variables, and we were interested in developing information inequalities regarding these random variables, control their entropies, and so on, right? To do that, what we did was we looked at the typical sets of these random variables in a larger dimensional space, and we controlled that geometry of those typical sets by using measure concentration. And then we translated that geometry back to information inequalities, okay? And if you think about it, we know that the entropy, the differential entropy, for example, of a continuous random variable can be regarded as the exponential growth rate of the volume of its typical set, okay? So in this sense, you can, in principle, kind of hope to develop information inequalities by studying the geometry of typical sets. But I don't think this is really something we have done too much, okay? I have seen too much. And maybe, I mean, this kind of a geometric approach can allow to make progress on other long-standing open problems in network information theory, okay? So that's all I want to say. Thank you.